data, but some of you have asked me to show a little bit about what we think, what we think your interaction for the homework should look like. So I thought I'd just give you a short demo of our reference solution. So here we have the graph with the teams and the games. So you can see the teams here are triangles, and the games are circles. And so what happens is, whenever I select a game, I simply get the game here in the Pac-12 game attendance bar chart, and the place where the game was played is highlighted here. So that works, of course, for any game. And whenever I select a team, all of the games that the team has played are highlighted. So you can see the updated bar chart here, and you can see the locations where the team has played here at the bottom. So that's basically the interaction. This should also work if you select a node here. But you can also drill down in the bar chart. So I can select a team, I can select a specific game, and then everything is synchronized.
I have a question about the label in X. Do we have to make it in the middle of the text? So, because I see it looks
what,
like
this
that.
one here?
Yes.
Well, the aesthetics kind of dictate that, right? Where will you put it? On the left side here?
Yeah, both.
Well, what do you mean? Like, I think it probably doesn't really matter too much if it looks like that, but it shouldn't be hard to position it in the middle. We had examples like this.
Because when I implemented my 30,000 is on the bottom, and my 9.
Oh, so you mean that?
Yeah.
No.
So that's
we will talk about this next lecture. Bar charts should always start at 0. So like you can't, you shouldn't show like, okay, 30,000 is 0. That is simply deceiving. So you should really start your scale at 0.
But I think the scale between 0 and the 30,000 is different between the 30,000.
Yeah, you're right. It could be. So we'll have to fix our reference solution in that case. But it should not be.
It should start at 0.
Yeah, it doesn't start. This looks like it starts at 20,000. Yeah, but it should start at 0. Yes.
So I'm also wondering, since your first label is 30,000,
Yeah.
how do you make the 20,000 and 10,000 go away, or 0?
Yeah,
like, where did they go?
I guess here what happened is probably that we used a nice option, or it could be that the scale starts at 21,000. I don't know the specifics now at this point.
No,
but
it's the minimum value of the attendance. The range is between the min attendance and max min. So
yeah, so like you can do this min to max, but I will definitely fix that. You should do 0 to max.
Like 0 to max of all the data, or?
Yeah, and that should stay constant, because otherwise
the scale changes.
Otherwise the scale changes, and then like here we have games with 80,000 player, with 80,000 or 85,000 attendance, and here we only have 60,000. But if the scale would change, these bars would look equally high. So that's not good, of course. You kind of want to have consistent scale in this case. Any other questions?
Do you know a resource, or is there a link to one that would... I'm in the process of trying to make sure that I link the data between things to, like, okay, if you select this object, you want to select this data point from this other part of the visualization, and I'm not quite sure how to begin doing that.
So this is supposed to be kind of in the stub. There is like a selected games array in the instructions, and that's the way you should, that's what you should do.
So updating that and then...
Exactly. Generally, there's tools like that, but these are more intricate libraries. There's cross-filter, and there's also this library that we're developing that does these things like that.
Okay, that makes sense. Thank you.
Yeah.
Regarding hover, is it just the force directed that needs the hovering?
No, everything hovers here.
Okay.
So you can see, like, I hover over every element, and I can see which games.
So what happens when you hover over the little dots on the map? I just want to see what should be displayed. all the games.
Yeah, all the games with comma separated. Like these are of course details. Like if you do that a little bit differently, that's fine of course. In a real life system, I would probably use a tooltip here, not really a here on top, because this is kind of like if you're interacting with a map down here, you don't even see what is going on up there. But this is just an exercise. So yeah, and of course for the bonus assignment is the bipartite graph. And there is really about, like we don't have a reference implementation for that, so you could really design what you're interested in. But what you should essentially do is create a layout that takes account of the separation between games and teams. There's examples if you Google for bipartite layouts, you can look that up. So you're kind of free to design your own solution there. But you shouldn't use you can use a force-directed layout, but you shouldn't use just a force-directed layout, and you probably won't be so very successful. Any other questions about the homework? Okay. So then, let's continue with an interesting effect called preattentive processing. Okay, maybe I'll just quickly go over what we had last time. Just pick to the highlight slides. So, yeah, we distinguish between the concept of perception and cognition, and so preattentive processing, what we'll talk next, is really in this perception area, and then we distinguish between looking versus seeing. So who can see the Dalmatian now? Who can't see it yet? Who hasn't found it? Okay. If you haven't found it, download the slides and take a look. It shouldn't be that hard to spot. And then we talked a little bit about the eye. The interesting concept here was really that we have good vision at one central focus point around the foeva, and then we have only very fuzzy vision at the periphery. So this is essentially if you would only look at one single spot, this is essentially what you perceive here. And then we discussed that this is how we perceive the whole world is actually by these rapid eye movements, that's alteration between fixations and saccades. And then we watched a video that kind of demonstrated how this eye tracking looks like if you, for example, read the text and so on. Then we talked about color. I guess the most important parts here were that our displays cannot display every single option, every single color there is. Our displays are built up of a combination of 3 pixels, and these are chosen within this larger space. And the colors that are within that triangle, that's what you can actually display. And that is of course true for print as well as for projections. For print, of course, you could use more colors, then you would not get a triangle, but some other shape. But for computer screens, typically you have 3 pixels. Then we talked about color labeling, and this will be also very interesting in the next lecture on Tuesday. How do we visualize nominal data? So the idea is really you should only use color, like hue. Yes?
I had a question about the limitation of the computer screen to show colors. Even though there is that limitation, I know that sometimes your mind will fill in the blanks. Can it still perceive, in a sense, all colors?
I would say the colors, if you take a picture of a color that you can't really capture on a screen, you would get an approximate of the color, and you would still understand what is meant by that. So the example I like is these super highly reflective colors, but it won't have the same effect on you. So if you see a color like this in real life, you will perceive it differently. You might be your attention might be drawn to it, for example, but you will still recognize it as a similar color on a computer screen. These things are really important, mainly if you compare them next to each other, because our perception is really good at judging relatives, but not so much absolutes. So if you see 2 different screens, if you look at the same website on 2 different screens, you will see that there's quite a difference in terms of how good the color representation is. Like if you have a professional screen that is calibrated versus like a super cheap screen. But it will just like make maybe your impression a little bit like you think, oh, that's not as nice as it could be, but I don't think it would be like a strict distinction. But of course, for visualization, it can make a big difference. So if you on these kinds of screens, on projections and so on, like you will hear me all the time say, well, you can't really see this here. Because the color range and the shades, the different shades that you can see on this kind of projection with like the lighting conditions here on a 1024 pixel monitor is simply not the same as you can see on a good screen. So that's where it makes a difference. Okay. I talked too long, the computer went to sleep. We'll come back up eventually.
None of the students went to sleep, so that's...
Yeah. You can see my mouse. Here we go. Yeah, and then we talked a little bit about the dangers of color maps, that, especially for continuous data. If you use a color map like a rainbow color map, it has these arbitrary gradients. Like here, you can. This looks like there is a strict gradient here. There is another gradient here. Like it looks like there's something in the data. But if you look at the just the pure saturation color map, or then we see that there is nothing there. Actually, this is a completely continuous field. And here you would see a couple of rings, where in fact these rings are not really there. So here we had an example of that effect. And this is actually really like you can measure how bad people are comparing a luminance color map to this rainbow color scale. Then we talked about color blindness, and it is pretty like a common problem for especially men, that lots of males have red-green color deficiency, and you can do these color tests. Here's an example, and this is actually, if we get to it, today's design study. The issue here is really that you can't distinguish, if you're red-green colorblind, you can't really distinguish, for example, between those two. Well, they mean something completely different. Okay, and then we talked about the relativity of our perception. So, like what we perceive is always very dependent on the context. So these squares are always of the same color, but just because we have a gradient in the back, we kind of understand them to look differently. Yeah, we had this corn sweet illusion and other illusions. So here we just like expect, like our brain automatically computes the lighting. Like we understand the situation. Like the lighting is probably coming from top, so that the top cube here should be darker in its actual color, because we expect the lighting to come from top, and we expect here to be more of like a shadowy environment, and therefore we kind of and this is of course reinforced strongly by the shading here, but these are actually the same color. If we add this barrier here, we can see that those are actually the color, and this is just because we kind of interpolate the lighting. So this was what we talked about last time in terms of perception, and now let's continue with preattentive processing. So preattentive processing is really about properties of a visualization, or let's say not of a vis, but of any picture that you kind of perceive really, really rapidly. So within 200 and 250 milliseconds, you will have spotted preattentive features in a picture, and it's very accurate. You won't miss it, and it processes in parallel. So it doesn't matter how many symbols there are. If one of them is preattentive, you will immediately see it. So it's called preattentive because it happens before focused attention, it's really, as I mentioned, independent of the number of distractors, and the opposite of it is sequential search. So just to give you an example, if you look for a specific word in a text, like if you're looking for the word color in this text here, you would have to like look through it. This is not preattentive. But if I were to highlight this word in red, you would immediately see it. This is the idea of preattentive processing. So here is an example. The difference in hue, everybody spotted this red dot instantly. You didn't have to look through these points to think about which one is the red one. So that works nice. And we can clearly also see that there is no such point here. This also works for difference in curvature or form, but as you might have noticed, it doesn't work quite as quickly. So you were able to spot the circle here, but it took you a little bit longer. But you still didn't have to go through every single rectangle to check, is this a circle or not? It doesn't work for combinations. So in this case, we're looking for the red circle. Raise your hand if you found it. Yeah. So it took you, like you really had to go through it, right? So you didn't immediately perceive it. So if you have two preattentive properties, like shape and color, you can't combine them and still have them preattentive. So it's not valid for conjunctions. There's other preattentive properties. So we have orientation here on the top left. Then we have the length here. Then closure, size, curvature, density, hue, of course. This should be saturation, the bottom here. Flicker, this should be blinking. It does not. Yeah, it does when I click on it. Yeah, this is what you should see. This is now only an artifact of the GIF in the slides. And of course, motion. So motion is very preattentive for us, and you can see motion even in your peripheral vision, and that's of course again evolutionary. If somebody, like if a tiger approaches you from the right, you want to see it, otherwise you have an evolutionary disadvantage. So the kind of tasks that you can solve with preattentive properties is of course target detection, but also boundary detection. So detect, like see, like a texture boundary between two groups of elements. You could do region tracking over time and space, or you could do counting and estimation. So when I showed you the single red dot, you would immediately know if that there was one red dot. If I showed you 4 red dots in the mass of blue red dots, you would have immediately an idea of how many dots there are. You wouldn't know it's 4, but you would know it's somewhere between 2 and 7, something like this. So here, like our examples for that, number estimation. You kind of have a feeling quite quickly how many elements are preattentive here, and then boundary detection works good for hue, but it doesn't work again for conjunctions. So here we have red circles on top and blue squares and red circles at the bottom. If you look closely, you can see the boundary, but it's definitely not preattentive. And there's a hierarchy of preattentive features. So hue is very strong, as you can see here. Hue is stronger than other shapes. Like here we can see the boundaries quite well. And here it's not as easy to see the boundary. So like we first look for the for hue in this case. And there's more examples online. This is one of the recommended pieces of reading. And it's quite interesting to look through this and to read a little bit about it. You can do experiments where you can actually like try to where you can try to estimate how quickly you can actually perceive one of these elements. So I could increase the exposure time, and then I can try various things like shape. And you can see that it's harder to do shape in 400, let's go down to 200 milliseconds. So you kind of can tell when something is present for shape, but you're not sure if it's not present. Whereas for color, you're pretty sure that it's not present. At least for me. Yeah, so here are these figures. Take this with a grain of salt, this document. I agree with most of the things, but not with quite everything. So, yeah, you can take a look if you want to read more on this. Why is this interesting for visualization? Well, it's really important to draw people's attention to areas of interest. We will use this for highlighting. You use this for example, if you do the color highlighting of the game notes in your homework, you're kind of altering a preattentive feature and make them quickly recognize that there was something selected. It can also be used to express the similarity between two items or group memberships, but you must carefully design those visual features. As you've seen, you can't really do this with conjunction, so you only have a very limited vocabulary here. So you kind of have to carefully choose which features you want to use preattentively. And on the opposite, you shouldn't use any preattentive features or preattentive visual attributes for things that you don't want to stick out immediately. Yeah, we will talk more about focus and context techniques and visual encoding and so on next week. So another interesting effect, especially for interactive visualization, is change blindness. So like we are not super great at detecting changes in scenes. So we don't remember the details of an image across separate scenes, except in areas where we really focus our attention. And if we have an interruption, so if you, for example, blink with our eyes, or if you look somewhere else, this effect is amplified. And it's not really a failure of the vision system, because the vision actually processing it, but we kind of don't really guide our attendance to it. So it's more a failure of the cognition. And so the thing is that we don't store every single element. So let's say if I leave this room today, in 2 weeks I won't remember whether the chairs were red or blue. And if the chairs were to change while I'm drawing something, the color of the chairs were to change while I'm drawing something on the blackboard, I might not recognize it. So here is an example. Can you see a change between those two pictures? You should raise your hand if you spotted the change. 2 person, 3, 4, 5, 6, 7, 8, 9. So we kind of, about half of the class has now found a change. And if you look closely, there's no shadow in one of the pictures here. Here's another one. Raise your hand if you spot the change. Some of you, but still not everyone. I'll give you 5 more seconds. Okay, so take a look here at this box. So you can't see that change, and this one, of course, is very obvious. So here the flicker essentially attracts your attention. Here's another example. Raise your hand. One person, 2, 3, 4. So what you're doing is really, you're going through every single segment of the picture and try to focus your attention, and then you kind of realize it eventually. Look at the turbine here. And again, of course, if we show it like this, it's pretty obvious. So there's various theories of why this happens. It's overriding, so information that was not abstracted, that you didn't really conceptualize, is lost. The first impression theory, nothing is stored. We don't store pixels, but we only store concepts, and only those are committed to memory. Or the other concept is everything is stored, nothing is compared. We compare only when we are forced to, or feature combinations, the scenes are combined as long as they make sense, but not if they don't. And of course, influencing factors are the attention, like how much focused, like since I'm telling you that there's a change happening, you really pay a lot of attention. But if you don't expect a change, you would have much harder time to actually recognize it. The semantic importance of a changed object, so if there's only a single person in the picture and I would remove this person, then of course you would recognize it immediately. Or low-level object properties are overlooked more easily, like texture, color, and so on. This, of course, extends to attention blindness. So here it's not about rapid change, but it's really about your attention. So this is I hope you can hear.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
But how did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away. It's just a matter of observation. The real question is, how observant were you? Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
So if your sensory system works a little bit like mine, you didn't even recognize a single one.
I only noticed that there was a knight in the back, but I didn't notice it used to be a bear.
There's a couple of other videos that are just too fun to pass up. So this is again the change blindness one. Tell them, like, raise your hand, like I'm telling you, now something has changed rapidly. So, showing it one more time, and then I'm actually telling you what to look for.
It's pretty subtle.
And in contrast to previously, this is a
This one's easy.
gradual. Yeah, it's a gradual change. So it's not. We don't have an abstractor in between, but still, it's not as easy to spot. So look at the bottom right corner here. And you can see that the cornfield is mown in one picture, not in the other one. So this is just to illustrate that this doesn't need to be like, you can't even focus your attention and don't see this change. And there's another one here. I forgot which one it was, so. I don't see it here. Oh, yeah. So you can see the stone appearing here. And this doesn't only work for, well, I'll just let you. The title gives away what you should be looking for. So if you look at the woman's sweater, it actually changes in color. Now it's reddish.
So I'm colorblind, and that didn't even register.
Yeah.
Stupid lying movies.
And
this is a movie perception test. Watch this brief silent movie, and then I'll ask you some questions about it. You saw a person get up from a desk to answer a phone, right? Did you notice anything changed during the video? The video had two different actors wearing different clothing. Watch it again. Most people don't notice the change, a phenomenon known as change blindness. This video is from research by Daniel.
And then there's one attention.
This is an awareness test. How many passes does the team in white make? Go! The answer is 13. But did you see the moonwalking bear?
Yeah, so this is of course relevant for many things, but it's also interesting, relevant for visualization. So why is this important for visualization? You shouldn't, we must selectively pay attention to what is important to understand it, and you have to think about this when you design interfaces for your users. Our low-level vision is driven by object features rather than conscious effort to where to look, so like this preattentive processing. And our attention is driven by pre-existing knowledge, expectations, and goals stored in long-term memory. So like a very simple takeaway is don't do subtle changes in your interface if you want people to notice it. It's like make it stand out, make it blink, make it pop up. Now, blinking, it might be interesting if you want to alert of an emergency, but really take care when you design your interfaces that you don't assume that people pay constant attention to what you're doing. And may take care of your visual attributes, of course, and how you use them. Okay, so the last part of the perception lecture is on Gestalt Principles. And Gestalt Principles are essentially like observations on how we interpret real scenes, some concepts that are essentially in our minds about the world. And they were developed by Wertheimer and Vienna group of psychologists in 1923. These guys really came up with a lot of those. There's a couple of recent extensions that are also relevant for visualization, so I will talk about them. They also had theories about why they work, and they were wrong, but the description of what are the Gestalt principles, they were correct. So the idea of Gestalt principles are patterns that transcend the visual stimuli that produce them. So for example, connection, like if we connect two elements, that is like we see them as belonging together. If we enclose them, we see them as belonging together. If we have like a common color region, common texture region, we group these elements, or if we arrange them spatially, like we also group them mentally. Alignment is one of the Gestalt principles, and the common movement. So if these letters were to move like this, that would also be like one of the Gestalt principles. So it's really like very much about grouping structures. So in this case here, because of the proximity, we perceive this here as columns, but we don't really think of this as rows. These here, in contrast, are clearly perceived as rows in this example. And again, we have a hierarchy of features. So like here we have like a square of circles, and then we separate it spatially. And in this case, for everybody here, it's clearly those two are groups. And if we use color, like your primary grouping mentally is still these spatial separations here. So the position here supersedes the color. Of course, consciously you can tell, okay, there's a second grouping, like a second level grouping, but the primary grouping is clearly the position here. Grouping, linking by placing entities in close proximity is one of them. Similarity in general, like any visual attribute that you could vary, essentially lets us group things. Like here, we can see that these are grouped by color. So more generally, it's co-modulation of a channel, and we'll talk about channels like color, shape, size, value, orientation, texture, and so on in the future. So here we have co-modulation of color, co-modulation of shape, value, or we add a glyph. So these could all be our options for grouping things. Of course, we have the perception issues of color, so we can, like for preattentive processing, this works easily for those two. But if I have these many distractors here with different colors, it's not as easy to group those two anymore. So this can also be used, so like this kind of issues are of course relevant, or for like preattentive processing again, is also relevant for perception. So the size of colored object here is relevant. So like if you look at this screenshot, you can probably spot quickly 4 highlighted regions here, but in total there's 6. So there's one here and there's one here, and this one is harder to spot, of course, because of the contrast, and this, and of course it's reduced in size, and this one is harder to spot because of the size, and again, it's more in a more cluttered environment. You could also modulate everything else in an environment, so you could blur all of the other points, or you could darken everything around you. Some of the interfaces, like some of computer interfaces, do this darkening. I think Windows Vista, when they popped up a message box that wasn't aggressive enough for them, so they kind of also darkened the whole screen. And so these things, you should only really use them if there's only one objective, and it's drawing somebody's attention to exactly what you want to see. So in this case here, people want to highlight this particular button, but this is of course very aggressive. Like you really should have a good motivation for doing this. And you could do this with scatter plots. You could have a selection by blur, which works, isn't that easy to implement, and has some other disadvantages. So blur is only binary. You can't have multiple gradients of blur. People can't distinguish that. So here's a little experiment. Try to mentally group those. It's pretty easy. And these are also easily grouped. Then we also group by size. And we group by shape. However, as soon as we add connectivity to it, our grouping is obviously stronger for the connection lines here. So no matter which other principles we use, if we use a connecting line or a shared, like an outline or something like this, this is our primary grouping principle here. So in a scatter plot, for example, you could, like this is called connectedness, a surface that surrounds it, or an outline. These are strong features, strong grouping features. And you can use this in visualization. So here, this is an example of some of my work. And here we really use these lines to connect related items. And we could use color highlights, like we could add a column and simply show these are the selected items. But in this case here, we're really showing like the flow of things, the connections between various, in this case, elements in a heat map. Very clearly. Yeah, we kind of mentioned that, similarity, connection, and enclosure. And here it's we can clearly see that like if we only had the dots here, this would be harder to recognize, but since we have the connections, and if we enclose this, it's pretty clear which is which in this example. There is a lot of research there was a lot of research in this area. So, for example, there is a technique that is called bubble sets that shows you set relationships on top of any arbitrary scene with these bubble highlights, or there is line sets that simply connect related items with lines. And here these are kelp diagrams. They're similar to the line sets, but instead of having a continuous line, they branch off and so on. So that's some of the examples of recent research in this area. Another Gestalt principle is continuity. So here we are perceiving this as a rectangle occluding a circle. We're not perceiving this as a separated rectangle, maybe. We don't perceive it as a circle with this kind of shape or this kind of shape. We kind of imply that there is good continuation of a shape. So this is something like, this would be I guess an alternative solution, but obviously everybody thinks this is really just an occlusion scenario here. We assume that things are smooth and continuous. So like if we see the shape here, we assume that there is one shape and the second shape is a rectangle. So this is kind of our perceptual assumption. This is not. So if the reality is like that, you kind of have to make sure that people actually recognize them by showing, for example, this line here in red versus black for the other line. And it's easier for us to trace, for example, links if they're smooth and continuous. So if you compare those two diagrams, it's easier for us to trace the connections between those spheres if we have continuous lines versus if we have these angular lines. Here's another example of a piece of my research. Like here, this is kind of like a prototype, and here we kind of only draw straight connection lines. And they have, here we kind of change the angle and move it up and change the angle again. But the continuous example is much easier to trace them. Closure is something that we also kind of like our mind processes immediately. So like even there is no there is no line here, but we still perceive this distinct shape here and the symbol. And the same here, like there's no lines here, but everybody sees that this is kind of the end of the shoe. Like we interpret the closure in this case. And you can take this pretty far. You can see shapes only by hints of how their geometry looks like. That's a pretty interesting effect. Everybody can easily spot the rectangle, but in reality there's only a couple of circles with a segment clipped out. Symmetry is important. So like this somehow doesn't quite look right for us. This is clearly a figure and this is clearly a figure. And we're really good at spotting mistakes in symmetry. I'll have an example here. And again, a figure and ground example. So like we assume that things are symmetric like this. We don't assume that this would be shaped like this. Here is a common example that uses symmetry, like the population pyramid. If you like have a bar chart and on the left we see men, on the right we see women, and we plot I guess everybody should have seen this before, but here is the age. This is like the bars show you how many percent are in a specific age group, and then you can see where there are any you can see changes over how frequent or the percentage of people that are in a specific age group. So obviously this kind of deteriorates as people get older, and you can also see changes in symmetry quite easily. So let me spot one. Yeah, you can see quite an interesting change in symmetry here. So this is I don't exactly know what the data was here, but it says winter war. So yeah, anyway, we can clearly see these changes in symmetry quite quickly. So if you have data like this, where you want to compare two data sets, and if you have only two, of course, symmetry is a good way of doing that. It's not always clear, like you can create this ambiguous situation where figure and ground kind of alternate. So here, you can see, like who sees a cup on this picture here? Okay, who sees two faces? Enthusiasts both? Okay. So it's clear that you can either pick the cup as the figure or the faces as a figure. Or here you have, like MC Escher had many of those examples where you can like alternate between figure and ground and then smoothly transition and give some additional clues to alternate between figure and ground. So how do we apply this in visualization? So here is an example. Also, again, a piece of my research. I showed you this before, and here we kind of tried out these effects of how we can connect related elements to each other. And the first thing you can do is, of course, blurring. And this is hard to see here, especially on the screen with this resolution. But if you look closely, this fishing here is not blurred. This here is not blurred. This here is not blurred. So that kind of works, but it's not very strong. This is kind of strong, but maybe a little hard to spot here or here. Then we had the color highlights, which is easy to spot in many examples, except as I mentioned in these two here at the outlines. We could have this blinking, works, but well, at least here again the contrast isn't strong enough. Or you could draw these connection lines, and this is very strong, of course. One problem here, though, is that we have like occlusion. So this is a strong connecting principle, but we kind of deteriorate the readability of the text here. And that was kind of a research question that we had. Can we improve this? And we found the method and algorithm that is actually finds routes through like non-salient parts of an image. So we would simply give this algorithm a picture and the regions that are connected, and the algorithm would automatically route these links in a way so that they occlude a minimal amount of relevant information. So here it really looks for what are the salient regions in a scene, mainly by looking at changes in color gradients, and then finds like this is an optimization problem to find a cheap path that connects those elements. And we did a study and we did an eye tracking experiment on that, and we were able to show that this is much faster than any of the other examples here, and we could also show that this has to run its course before I can click. And we could also show that the R variant here didn't deteriorate performance, but improved readability. So that was just one example or a couple of examples of research in that area. So the takeaways about this lecture is really that knowing about perception is important for visualization and more generally user interface design. Of course, you don't have to be an expert in psychology. You don't have to know why things are happening in detail. And there's a lot of research going on in this area. But you kind of should think a little bit about how to choose your colors, how you would show relationships, how you would draw attention to important scenes in your visualization, and how to minimize the risk of overlooking something. So this is the end of the lecture that should have ended last week, or last Tuesday. So let's continue with data, but I think since I've been talking straight for 50 minutes, how about we start with a design critique to lighten things up a bit. So you can go to this document that I'm handing out here by the link on the bottom, or to the source here.
Oh, you got the That's great. Can you actually see much of a difference there, or is it?
Yeah, these colors are different here.
Grab it. Just grab it. Guess this is okay.
Okay, so I can see this reasonably well. So what's the questions? What is this?
What is the primary visual encoding in panel 1? I would say
Panel 1, all spin.
it's just color, I think, is the primary encoding, right? It seems to be the
Also size.
Size.
color and size. Do we think that these are good choices?
You know, I think they're fine. Except the size. The size is kind of funny. I don't understand what these little dots are. Oh, these are different illustrations.
What?
So these little dots represent different little organizations.
Oh yeah, that they're spending money. The difference in how they're spending, I think, right?
Yeah, more or less. So the largest amount, so the size encodes the amount, the color encodes the difference in change.
Yeah.
Okay, was that good? It's hard to compare them. I'd say that the size isn't as successful as the color.
Yeah. I think that I think they could have done better by doing like doing it backwards. Honestly.
Yeah.
Putting the size of it as the color.
Yeah.
And then put that the percent change is the size of it. Does that make sense?
But if you change the percent change, then how do you say this? Because this also, it actually has 3 encodings for the size.
Yeah.
If you flip the percent change on the size, then how do you say this is the amount spent? So then you have this really funny gradient. You have a really huge gradation scale of color.
Yeah, right. So it eliminates some of because there's a lot of variance in the amount spent on some of these things. Maybe it's easier to represent it with size and not have as many different colors.
Maybe it should just be a gradation of white to red, or white to green, so it's a shade of green instead of green to red to whatever that is. So if they 86 to 1 or gone to just a gradation of one color, then you can see, you can say this is over here, dark red would be $1 trillion, and over here would be $1 million.
So what do you think that creators wanted to do with this? What is the goal of this visualization?
I think the biggest thing is to shock us. How much are we spending? Who's trying to spend
I think
more?
it's trying to show how much is being spent.
Yeah,
that's what I
quite interesting.
I think it's the tabs on
so here's the types of spending. This is a lava lamp. Look at this. It's like a lava lamp.
What is the separation?
So the separation of the types, what they have to spend and what they can choose to spend. And here's another thing, when you switch between these, like without knowing any, if you go like this and you go, oh, well, what's that dot? And you go and do that, you can only track 1 or 2 dots, so you have to go through and then rediscover what each one of these things was again. And I think that's hard. There's no
Yeah, so I guess
There's no continuity between transitions. So,
Do you think it needs to have animation?
well, it does have animation.
Right, I'm asking because that's one of the questions.
Oh, that's the thing.
What do you think of the use of animation in the process?
I don't think it's successful, but I think it's necessary. If they just went from this to this, you'd be out of luck. You'd be real lost real quick. At least you can see movement.
You're not sure like what is bigger than
And I don't know if this is intentional, but you lose all these little teeny things.
like you said, you're
they kind of get
military.
The Forest Service, you're never going to find the Forest Service here. Never. What would be kind of cool is if you had an index on the side.
Okay, so being
this
able
is
to
the Forest Service, and you click on it, you can watch it flow back and forth.
Yeah, it'd be nice if they had maybe some things that you could click on that would say that would then highlight the circle, like you can mouse over the name of the department or something, and it would be like, oh, that's this one.
Yeah, if you could click on military spending and watch it travel between.
Yeah, that would make it a little bit more salient between the different panels because you'd be able to figure out things better.
Yeah, so my assumption that
So we go here. What if I want to know about the military spending? That I think that was kind of successful. This is a change in discretionary spending saying, oh, that's a really weird thing because they've got, okay, so this is, in this scale, it's the color shift. This is more, this is less spending. When you go here, they change the axis. So this is more spending, this is lower, it's less spending. So.
Okay, so
I think the colors mean the same thing.
let's talk a little bit
So
about
it's
this.
kind of like doubly saying the same thing.
So what is the primary, or what are the
So you
main
notice the
visual
darker
encodings
red
that
is
we're
on the
using
bottom.
in this first view here?
Color, position.
Color, size, and position. Okay, what does each of those mean?
Position?
Position and color mean kind of like the same thing, because like if you're at the top, you're going to be green because you have an increase, and if you're at the bottom, you're red because you're increase. So it's like it's a redundant model.
Yeah, okay, that's good. What, like, how faithful do you think position is?
Not very.
There's no indication of how faithful it is at all.
Yeah.
It's just grouping, not really.
Yeah, so this is so what do you think, how is this implemented? The positioning here.
Just like a force directed.
Exactly, this is like a force-based algorithm, so it's not, like the position can, like indicates the same thing as the color, but you can spot that this little dot here, for example, is a little bit darker than the ones up here, for example, and if I were to move this around, it actually moves up. So yeah, it kind of gives you a hint, which is fair, but it's not like an absolute thing. Okay, so we talked about color. So what color and position that what is it that they actually encode? Exactly. And the size?
The overall size.
Yes. Great. So do you think these are good choices? Yeah, so we talked about the red-green effect, of course, so the color is difficult. Bubble size, I guess it's, well, you could argue that you can easily spot the big ones and you get a good feeling for it. It's not necessarily the most effective visualization. Like an interesting point in the data, I thought, is that the interest of public debt is the third largest position. It's bigger than military spending. I wasn't aware of that until I saw that visualization. So if you like switch through these panels, do you think those are like effective? Like this particular visualization here? Like what is the point of this this panel here? One person at a time, please. Like, you wanna?
I just said it's now divided into mandatory spending, which is Social Security and all those other programs, and discretionary.
Yeah. So I guess the point here is really to show the people where there is liberty to actually change something like by the government, whereas the other ones that are here, you don't really, you can't really change that. And you might notice where are the predominant cuts? Yeah, so you can see that like there is an increase in spending in many of the mandatory spending ones, and there's a decrease in spending in many of the discretionary spending ones. So that is probably what they decided to do here. If you look at this panel here, what do you think? What is encoded here? Yeah. So x-axis seems is I think it's by departments or something like that, but you kind of have to guess that. Yeah, it's by interior. So it doesn't really label it clearly. That's an issue. How is position now used?
It's redundant with color, like this slide.
Yes. But in this case, it actually is a faithful representation of the data. So in this way, it actually does correctly encode the absolute values. With the exception of here is a broken scale. We have 26% or lower, so you kind of have to be aware of that.
Some circles are on top of each other.
Yes, that is one of the issues that happens if you combine like size and position. So of course that can happen, but I think they're doing a decent job in ordering them correctly. So you could easily hide many of the points here, but since they're ordered on top of each other, that kind of works out. But it's not that easy to achieve that. What do you think about the use of animation that we have here between all of these panels?
It's like a lava lamp.
Yeah.
It's eye-catching, it's kind of cool.
Yeah. Yeah, it's not like maybe, it doesn't really tell you much, but it's intriguing, and it doesn't really distract, I think, either. So
I guess it makes it clear that this is only showing the discretionary.
Yes, that is true. That's a good point. It says in the title, but if you look at the animation, that is helpful, yeah. Especially good if you transition like from one step to the other. If you do it like this, it's less obvious, obviously. And if you look at this panel, what do you think about that?
Some of the things like education, well, agriculture is about 3 times as big as education, but they look about the same size.
Agriculture is okay. Yeah. Yeah, that's true. And the reason for that is?
Might be a lot of room.
No?
At the empty circle.
Yes. The problem is that they visualize income the same way they visualize expenses by size. So here, empty circles show income. And that kind of like completely screwed up your perception of what is going on here. So this is really the main objective, the main objection I have to this visualization, how they show income. That is really...
If they show income, why not show income tax?
Well,
that would be a really big circle.
Yes, that would be a big circle. But yeah, so I guess it's department-centric. But the problem here is really the... in this case, this was designed for spending. We also need to show that there's income from these departments. Maybe not a good choice. So how could you, for example, fix that? If you say you want to stay with this primary visual encoding, at least you want to do most of it still with the circles, what could you do? Any ideas? Yep.
You could kind of separate it out, so it's separate proximity away from them, and that way, like, I mean, health and human services, that big bulk gets pushed way up there, and it's really not too much different from Social Security. There's a lot of other political bubbles. If you move that, it doesn't get nearly as extreme, so just kind of separating them so that the physical dynamics of them don't interact with each other.
Yes, that's a good idea, and you could even label them separately. So you could say, here is the income bubble, and maybe you could break down the income, and then you could have next to it the outgoing bubble, and maybe you could add an extra illustration at the bottom, like the difference between income and spending. That might be a faithful representation here, yeah. Of course, you could do this with bar charts every time, but but it would be less fun to play with, and I definitely agree that this, yeah, might attract less readers. So, who has a strong opinion of like or dislike, and if you want to comment?
I think it's the best of the three that we've shown.
Of the 3 design studies we did? Yeah. Which of the panels do you like most? The departmentals, this one?
Changes.
Yeah. I think this is the most faithful, like this is the like a visualization technique that really focuses on the data. The other ones are more illustrative. So I'm not saying that they're bad, but this is really a data visualization. The others are too, of course, but this really puts the data first.
It does make you wish you could see the non-discretionary spending as well, because you only get to see this one.
Yeah, that's true. That is definitely true. As I mentioned last time, this was the first visualization that the New York Times did with D3. This was 2013. They then hired the creator of D3, Mike Bostock, as a graphics editor for them. He has since left them to work full-time on D3, but we will see a lot of New York Times examples in the class, because I think they're probably setting the bar for how you do visualization in journalism, and we will see a couple of those. Okay, so we have like 15 minutes left to talk about data. I will of course continue next time with the lecture on data, but let's start with it. Okay, so a couple of terms. We have data set types. So what can we visualize? What can we collect? How can we what can we collect about our environment? What data is available? What are these data set types? So these are tables, networks, fields, or geometry, essentially. It's like tables are, as you can all easily imagine, they are simply combinations of rows and columns. Networks show you relationships. Fields are sampling or somehow describe a continuous phenomenon. So if you want to measure the temperature in a country or a city or a state and so on, you kind of have to define certain points where you measure them. But of course, every single point in space has a temperature. And geometry are things like maps or shapes and so on, and positions. Derived from these, from the table itself, are multidimensional tables. So you can have them, you can think of them as cubes, but it could also be higher dimensional. And networks have many special types, like for example trees, and we'll talk about these special types of networks and tables and so on. And then, so these are the data set types, and then we have data types, which are the fundamental units. So I could have temperature, for example, as a number, and that could be in a table, it could be associated with a node in a network, it could be in a field. It doesn't really make sense for geometry, but there's a difference between the data set types and the data types. So the combination of data types makes up the data set types. So here we have like the general data types. We have items, attributes, links, positions, and grids. We'll talk more about these in the following. A big distinction is between structured and unstructured data. And in this class, we will spend about 90% of our time talking about structured data. Simply because the way to analyze data, like if you have unstructured data, what you do is you create structure to analyze it. So this process of creating structure is, for example, something that okay, let's start. What are examples of unstructured data? When you don't have a predefined data model. So for example, text on a website or in a book and so on is unstructured, largely unstructured. You have, in this text, you have interspersed facts, you have dates, times, locations. What is also unstructured are videos or images. Like an image can contain any kind of information, but it's not easy to access for a computer. It's not structured. For us, it's of course easy to access as humans, and the same for video, but not for a computer. So what you do with unstructured data is typically translate it into structured data to do any kind of automatic analysis on it, or also to do visualization on it. So for example, if you have text data, your first step to visualize text data would be some kind of natural language processing or text mining that you do sentiment analysis, keyword analysis, heuristics, trying to extract concepts, trying to extract categories, or just to find simple relationships or to count words. Most simple one, counting words. And videos and images, of course, you first need to do any kind of image classification. You could do simple things like creating a color histogram and then pick all the mainly red pictures, or you can do more fancy things like object detection or scene detection or anything like that. So the reason why we don't talk a lot about unstructured data is really that you need first to do this translation process from unstructured into structured data, and these are all research fields of their own. So there's lectures and many people working in these things. So we will talk about some specific visualization techniques for images and for text and so on. But really the hard part and the science here is really in creating this structure from the unstructured material. So we'll focus on structured data where we have known data types and we also understand the semantics. I just wanted to give you an example of a visualization of a text visualization. It's a little hard to read, but this is a paper from 2009 and it's called PhraseNet. And this here is a network structure that was derived from the King James Bible based on the relationship between two entities, X beget Y. So in this case, Abraham beget Isaac, Isaac beget Jacob, and so on. And so what you can see are kind of these family relationships, who is whose child, and this was automatically created by a very simple rule. Looking for this X beget Y rule, we kind of derived the network structure, and this is how the network structure was visualized. And the other thing that is encoded here is the size, like how important or how often, how frequently are these people mentioned in the Bible. And so you can see that Azariah and Obed and Abraham and so on were more often mentioned than here at the bottom right. Well, I can barely read this, Solomon, and so on. This is a simple example of text visualization. Here is a fun example for that. Here you have X as Y. So like the sailor's wife, for example, would be a pattern that matches this this query here, and it uses a library of 18th and 19th century novels. And the relationships are interesting if we look at the use of bride and wife. So here we can see the banker's wife, the ambassador's wife, the father's wife, the merchant's wife, but the freebooter's bride, the pirate's bride, the bandit's bride. So these shaded characters don't seem to be married, they seem to have brides, not wives. This is the kind of things that you can do with this kind of visualization. So more on this kind of stuff will be in the lecture on text and document visualization. Here I have a data vector, Basel 7S pair. What does it mean? We don't know. Like, this is data, we know that this is a string, this is a number, this could be a category or could be a string, then we have another string. But we don't know what it means. So it could be a name, a city, a fruit, the height of somebody, the age, the day of the month, or and so on. So what is missing here is metadata that defines its semantics. And these metadata is typically given in columns. So here is an example. We have an ID, we have name, we have age, we have shirt size, and we have favorite fruit. And now we know how to interpret this data. So this is, of course, always important to understand what the semantics of a data set is. And then the data types themselves, they're the structural or mathematical interpretation of the data. So things like item, link, attribute, position, or grid. And those are different from data types in programming here. Like a link could be an integer pointing to an index of something else. An item could be a string or a number. A position is probably referred to by a combination of integers and so on. So these data types are different from what you would have in programming. Just a word of caution here. So an item is, we distinguish between items and attributes. An item is an individual entity, something discrete, like for example a patient, a car, a stock, or a city. An attribute is a measured and observed property of an item. So for example, for a patient, that could be his height, his blood pressure, his temperature, and so on. For a car, it could be its horsepower and make. So in statistics, you would call these as the independent and the dependent variables. So these are the independent variables here, and this would be the dependent variable. So you kind of need an independent variable to measure a dependent variable. And typically, like the standard representation is that we have the items in the rows. Like here in this case, the item would be a person, and then we have the attributes in the columns. About the other data types, links express relationships between two items. For example, friendships on Facebook, or interactions between proteins, or neighborhood in a city, or anything like that could be a link. Positions are locations in 2D or 3D in the case of spatial data. For example, the pixels in a photo, the voxels in an MRI scan, or latitude, longitude on a map. And grids are a special type of data type that is essentially a sampling strategy for continuous data. And we'll have a lecture on grids. For example, how many voxels are there in an MRI scan? How regularly are they? You could also think of the positions of weather stations in the US as an irregular grid. So we have, like, they're not exactly at a specific longitude and latitude positions, but they're rather arbitrarily positioned. So this would be an irregular grid. So let's talk a little bit more about the dataset types. Let's start with tables. In a flat table, we would have one item per row, and each column would be an attribute. And we would have a unique unique key. This is important, which can also be implicit. And typically, a data table, like a flat table, doesn't contain duplicates. A multidimensional table could then have like indexing based on multiple keys. So here is an example. So this would be a flat table. We would have the item here. Then we would have the values here. This would be the keys. And together, those would be the attributes. And as you can see, the keys here are really just random numbers. And as I mentioned, they could be implicit. So the key could be the index of the row. It doesn't need to be an explicit ID. This is a multidimensional table. So here we have keys, like patients are keys. These are codes for patients of a cancer data set. And then we have genes as keys. So like this is, for this patient, this gene has this value. And this is a multidimensional table in that case. Of course, we can only show, in this 2D structure, we can only show like we can't show multiple attributes. So we kind of, in this case, we can only show one attribute, then we would have multiple tables to show more attributes. There is many ways you can visualize tables, and we will, like, most of the data that we've been working with so far has been tables. There is parallel coordinates, there's heat maps, there is this kind of matrix diagrams. You can have table-based visualization where you mix position and bar charts and so on. We will have a dedicated lecture on tables and high-dimensional data in the second part of this class. You can click on these examples, and this is a D3 implementation of parallel coordinates. Here we have various dimensions. These are cars, like you have the miles per gallon, cylinders, displacement, power, weight, and so on. And each of these lines is a car, and they connect, like, and by connecting through this, across these various dimensions, you see the properties of a car. So we can see that cars with a high miles per gallon value typically have not a lot of cylinders, for example, here. And they have little horsepower, and they're not very heavy. This is the kind of relationships that you can see here. And I guess this is a good point to stop for today. I will continue with this next Tuesday. Thank you for being here, and until Tuesday.
That was really good. I like that one.
Yeah, it's good. It has some disadvantages.
Well, it's hard to follow any individual, but you can see trends really nicely.
You can follow an individual if you just select an individual. So you need interaction.
Yeah, you need to be able to say, this is a particular car.
Yeah. So there's a lot of research on this stuff. One of the disadvantages, of course, that if you don't use highlighting, you can't see relationships between, like you can see a relationship between neighbors, but you can't see a relationship between this one and this one here. Easily, like that.
Yeah, it's hard to follow.